Okay, this is the last video, radiative heat transfer for the black surfaces. So previously we already learned about the view factors, and in this video we will use that all of that, not all, some of them based on the problems or the questions. And we apply that view factors relationship, view factors rules into these videos, into this chapter lah, subchapter, the last subchapter, to calculate the radiation heat transfer. Okay, so this radiation is for black surfaces, so if we want to find what is rate of radiation, let's take a look at these equations. So we refer to this figure. We want to find what is the Q dot 1 to 2. So which means from the surface 1, what is the net radiation? Okay, rate of radiation. Net rate of radiation from 1 to 2. So we have to find what is Q dot 1 to 2. So to find what is Q dot 1 to 2, we know that if that surface 1 radiates energy, it will transfer the energy, and then some of the energy will reflect back to this surface 1. So Q reflects, for example, and then this is Q emit. So in order for us to find this Q, we have to minus QE with QR. So that's why radiation leaving the entire surface 1 that strikes surface 2, so leaving 1 to 2, minus, we have to minus in order for us to find what is the net radiation from 1 to 2. So minus with radiation leaving the entire surface 2 that strikes surface 1. So in order for us to find the Q net, we have to find Q emit, which means that emit from the first from the 1, and then we have to minus with Q radiates. Okay, Q reflects, reflects from surface 2. I means reflects is it will reflect and turn to 1. Okay, therefore to find what is the net radiation from 1 to 2, we have to minus both of these. So from here we know that radiation leaving the entire surface 1 that strikes surface 2, equation is A1 EB1, so E black body 1, okay, times with F 1 to 2, because we have to find what is the view factors from F1 to 2. So this times with black body radiation emission, okay, minus with A2 area 2 times with emissive power B, okay, black body at 2 for 2, and then F2 to 1, so 2 strikes back to 1. Okay, so applying the reciprocity relationship, okay, we know that F1 to 2 and F2 to 1, so A1 F1 to 2 equal to A2 F 2 to 1. So we can actually substitute A2 F2 to 1 to A1 F1 to 2. So if we substitute, it will becomes EB1, so F1 to 2 minus A2, A1 EB2 F1 to 2. Okay, so equation for EB is what? So EB is Stefan-Boltzmann times with temperature to the power of 4. Okay, this is black body emissive power, so Stefan-Boltzmann times with temperature to the power of 4. So therefore we substitute here, so A1 Stefan-Boltzmann temperature, this is B1 for temperature 1, therefore here is T1 for F1 to 2 minus A1 EB2 here. For the EB2, therefore T will be T2. So Stefan-Boltzmann T2 to the power of 4F 1 to 2. So from here we can see that A1, we can simplify this equation, okay, F12 and F13. So therefore it will becomes A1. So A1 Stefan-Boltzmann, sorry. So F1 to 2 in a bracket T1 was to the power of 4 minus T 2 to the power of 4. So the equation becomes like this lah. Okay. So the net radiation heat transfer from any surface I of this enclosure is determined by adding up the net radiation heat transfer from the surface I to each of the surface of the enclosure. So if you have more than one surfaces, then you have to add up all those surfaces in order to find the net radiation heat transfer from surface I. So for example, if you have one surface, another surface 2, 3, so here is 1. So if you want to find what is the Q dot, therefore you have to find what is Q dot 1 to 2 plus Q dot 1 to 3 in order for you to find what is the net radiation heat transfer from surface I. So which means this is Q dot 1. Okay. Now let's take a look at the question. Okay. Consider the 5 meter times 5 meter times 5 meter cubicle furnace shown in figure. So in this figure, this is figure for furnace whose surfaces closely approximate black surfaces. So the base, top and side surfaces of the furnace are maintained at uniform temperatures of 800 Kelvin, 1500 Kelvin and 500 Kelvin respectively. So first, determine the net rate of radiation heat transfer between the base. So base is 1 to the side surfaces 3. And then the net radiation heat transfer between the base and the top of the surface. And the last one, the net radiation heat transfer from the base surfaces. Okay, what is the Q dot 1? So question A, Q dot 1 to 3. Question B, Q dot 1 to 2. And question C is Q dot 1. Why do we only consider Q1 to 3? Because we have four surfaces here. So 1, 2, at the back is 3, okay, and 4. Because all of these 4 have the same dimension, therefore we only considered 1 only, okay, at 3. The side surfaces only at 3, only 1 surfaces, okay. If all those 4 have the same geometries, okay. If 2 of them have different geometries like this, for example, for example, you have these kinds of arrangement, for example. So therefore, the 3 could not be the same as 4. 4 and 5 at the back will be the same. So you only consider only 1, only 4. And 3, 4, 5, 6. So this 6 is alone. And then 4 and 5 can be combined and calculate only single side. And then 3 alone. Okay. Now we have rectangular where we have 4 different sides which have the same geometries. Therefore, we only considered only 1 surface. Okay. So now let's take a look at the first question, A. So for the A, we have to find what is Q dot 1, 3. Okay, from the side to from the base to the side surfaces. So in order for us to find Q dot 1 to 3, okay, is equal to A1 F1 to 3. Okay, Stefan Boltzmann T1 to the power of 4 minus T3 to the power of 4. Please refer my explanation on this slide. Okay, why do I wrote down that kinds of form, these kinds of equation? How do I get this? Okay, now what we have to do is to find view factors for F1 to 3. So F1 to 3, from summation rules, we know that F1 to 1 plus F1 to 2 plus F1 to 3 is equivalent to 1. This is summation rules. Okay, now since the base of this question, the base of this furnace is flat, therefore F11 is 0. So F11 equal to 0. So we have only F12 plus F13 equal to 1. Okay, now we take a look at 1, 2 and 1, 3. Can we find any of these values from the figures, charts? So we have this. Of course, no, because this is not cylinder. Is it this? No, because cylinder, horizontal cylinder. About this? How about this? Yes. And this? No. So we will use these kinds of graph. Okay, maybe you can use these kinds of graph. Okay, it is up to you lah. So I will use this graph to determine what is the value for. So as we can refer to this figure, so our number 2 is at the top. So if you refer to this figure, you will find 1 to 3. And if you refer to this figure, you are referring to 1 to 2. So we have this and bottom. So what you have to do is to find L1 over D and L2 over D. Okay. So plug in all the values. Okay. L2 over D. So L2 is from here to here. So let's take a look at this. And all of this is 5 times 5 times 5, which means all the same dimensions, length, height, and width. So 5. So for the L1 over D is 5 centimeter over, is it centimeter? Meter. What about diameter? Diameter is the length. Okay. So the length of this cubic is 5 meters. Sorry. So cancel out, you get 1. So L2 over D is 5 over 5. Cancel out, we get 1. So 1. So you drag, you draw a straight line up, and then find 1. So here is 1. So 1 here. Intercept at this point, so you draw a line and find what is F12. So I get my F12 is 0.2. Okay, 0.2. So my F12 is 0.2, therefore F13 equal to 1 minus 0.2. So you will get F13 is about 0.8. So after you get this, substitute the values inside this. So Q dot 13 equal to, so the area 1 is 25, 5 times 5 meter square, times with 0.8 and then 0.8 is for F13, and then times with Stephan-Boltzmann 5.67 times 10 to the power of minus 8 watt per meter Kelvin, and then times with 800K to the power of 4 minus 500K to the power of 4. So you will get Q13 is equivalent to 394 kilowatt. Okay, that is number 1A, Q12. So now we find Q12. First is Q13, sorry. Second is Q.12. So to find Q.12, so A1, okay, A1 times with F12. And then Stephan-Boltzmann, T1 to the power of 4 minus T2 to the power of 4. So you substitute because we already determined the F12 values. Okay, 25 meter square times with F12 is 0.2. Okay, Stephan-Boltzmann 5.67 times 10 to the power of minus 8, and times with temperature 1 is 800 Kelvin to the power of 4 minus 1500 Kelvin to the power of 4. Okay, so you will get the value of this is about negative 1319, so kilowatt. So the negative sign indicates that the net radiation heat transfer is from surface 2 to surface 1. Okay, so the last that we need to do is Q.1 from the base. What is the net radiation from the base? So what we have to do is we have to sum up all those Q.13 plus Q.12. So Q.13 is plus another one is Q.11. So normally 11 we cannot calculate because F11 is equal to 0. So like this, Q11 is A1 F11. Okay, Stephan-Boltzmann T1 to the power of 4 minus T1 to the power of 4. So both of these have the same values, and then it will cancel out, and Q.11 equal to 0. So therefore the Q.11 is equal to 0. So Q13 is about 394 kilowatt. You have to plus with minus. So please bring that minus with you, okay, in order for you to get Q.1. So negative 1319 kilowatt. So what you get here, your Q.1 is equivalent to negative 925 kilowatt. So the negative signs indicate that the net radiation heat transfer is to surface 1. Okay. Please remember that when you are calculating the Q dot, please make sure that you already change the temperature to Kelvin. Since the temperature inside of this is not in the range, therefore you cannot substitute in degrees Celsius. So you must remember in radiation, this T must be in Kelvin. Okay. That's all for the radiation, and I really hope that you will understand all the lecture of my lecture, and I really hope that you do well with your final assessment. And if you have anything to ask, you may WhatsApp me, or you may SMS me, or whatever platform that you think that it is easier for you to contact me and easier for you to understand. I'm really happy to answer your question. Okay, please revise back all those videos, and good luck. Thank you.